Hey, this is Vico. Welcome back. Let's build a new front-end framework in Haskell. You may now ask, why another front-end framework? Why use Haskell for the web? Why use Haskell at all? But these are all the wrong questions entirely. There's one simple answer. Just for fun. Or if you want to know the truth, I dream about monads at night. Anyways, so why Haskell for real? Have you seen something this expressive, like ever? No? You can't even read what's happening? Well, in this case, just check out one of my older videos about why this computes the Fibonacci sequence. Anyways, that's besides the point. What I wanna say is that I really just like the language and the challenge associated with porting it to the web. Everything you can see in this video, from the slides, the script and the source code of the end product, can be found on an openly available repository on GitHub. The links can be found in the description below. And yes, I got inspired by No Boilerplate's fast technical videos, which you can also find in the description below. And now let's finally get started. So what is the ultimate goal here? We want to have something like this that works in pure Haskell. Therefore, it should fulfill the following points. There should be an easy and descriptive way of creating the UI. There should be an easy way of callback functions for button clicks, for example. This also implies that it should support input handling. It should be blazingly fast. Also, the whole thing should not use HTML, but rather render to canvas to provide optimal performance. This is also the approach that Flutter takes, and this splits it loose from CSS and HTML completely, allowing us to define our own custom layouting system as we please. That's just a lot of stuff. Therefore, today we'll only talk about drawing to the HTML canvas, which is already gonna be quite the ride, so buckle up. So the first step is compiling Haskell to Wasm. For that we need a version of the glorious Haskell compiler that compiles Haskell source code into a Wasm reactor module. Luckily there's exactly that, and you can find a lot of information and documentation about the whole thing in this repo. As a build system, I chose Nix because GHC Wasm Meta literally exposes a Nix flake that we can just pull to get a GHC version, which can be seen above. Nix is a big topic, and if you're interested in it, just let me know in the comments below. I will certainly make a video about it in the future. Here we fetch the Cabal wrapper of the GHC version, which allows us to use the Cabal build system for Haskell to build our project. Now let's have a quick look at the .cabal file that specifies which functions we export. Here we can see that we include some C sources in our project that are just used to initialize the Haskell RTS and garbage collection. Wiser will be used to make sure that before loading the Wasm module, these configurations will be run. Below we can see that we just export a Wasm reactor module, which is basically just a library in Wasm terms. We can also define which functions we export. The second code block shows the definition and declaration of the exported malloc bytes function that will be used to allocate memory on the Wasm side. Notice that we export malloc bytes as a C function here. The reason for that is that Haskell first generates C functions before actually generating the Wasm side of things. This is possible due to the good FFI interface between Haskell and C. Let's have a quick look at the build script, though it is incredibly simple. First, we use the custom GHC version to compile our project to Wasm. Then we run Wiser to make sure that the Haskell runtime system and garbage collector get initialized correctly. Finally, we just move our library to the front-end source directory. Running this using Nix develop ensures perfect reproducibility under all circumstances. Nix makes sure you can build your project on any system with Nix installed. Thankfully, Nix is available on all major platforms. Enough, I'm drifting off. Here you can see the JavaScript code that is actually calling these exported functions. First, we can get the export from the Wasm instance object. Then we are allocating enough bytes to buffer the entire canvas. Afterwards, we can call draw. It basically fills out the buffer with one static color. Real programmers don't do reference pointers. Real programmers poke their pointers. Anyways, after filling the buffer, we construct a uint8 claimed array using the start pointer as an offset into memory.buffer. This is basically the buffer containing all the linear memory, which means all of the memory available to WASM. After that, we can fill the canvas with the data. Now let's have a look at the result. Well, what did you expect? It's a gray rectangle, but it perfectly shows that our proof of concept is working. We were able to draw an image from Haskell onto an HTML canvas. Well, that sure was fun. Next time we're gonna get started building a small interface library for actually rendering something. So after finishing the work of this video, I realized that it won't be as easy as I thought to get a library that efficiently draws on the canvas into WebAssembly. The issue here is that when doing that efficiently, we use the GPU, which is not possible in pure WASM. Therefore, we would need to use something like WebGPU, which basically eradicates the need for WASM and therefore Haskell altogether. Anyways, I did what I wanted and successfully compiled Haskell to WASM, and it works very well. Therefore, I would call this project done. But now, welcome to the I like section, where I will quickly talk about technology that I found recently and find useful. This time it's gonna be Excalidraw. It's perfect for getting quick sketches out, and it allows handwriting and exporting to SVG, which is a big one for me. One graphic from this video was made in Excalidraw, and it was a breeze. And of course it's open source. Thank you for watching, and until next time. Next time I hope I tackle something that I can actually finish.